So if there are no questions, then let's talk about the buffer solutions. Now, these buffer solutions, they are solutions that do resist changes in pH when a small amount of the acid stroke base is added to them. You have your solution, okay, and it is at pH maybe 4.5. In one solution, when you just add a drop, just a drop in this solution, the pH will change from 4.5 to around 6.5 just by adding a mere drop. But in another solution, if the pH is at 4.5 and you add just a drop, okay, the pH remains, or it just adjusts a little bit and it becomes 4 point maybe 5 1. It just adjusts a little bit, but it resists changes in pH when a little base or a little acid is added into it. So now, you should be wondering, how do they do it? And which types of buffer solutions do we have? We have two types. And the first one is the acidic buffer. And this acidic buffer consists of a solution of a weak acid and its conjugate salt, or its salt that is formed between a strong alkaline solution and that weak acid. You have a weak acid, okay? Think of weak acids. You can have, carbonic acid, it's a weak acid, okay? Carbonic acid, it's a weak acid. As you can think of acetic acid, it is also a weak acid. And its salt that is formed by reacting that acid and a strong base, or you can say its conjugate base, or the conjugate base of a weak acid. For example, when we react this with sodium hydroxide, we shall form sodium, probably hydrogen carbonate. Okay? When we react this with, we shall probably form acetate. So a solution that contains both, okay, the acid and its salt formed by reacting it with a strong or with its conjugate base, it becomes an acidic buffer. And this solution resists or can resist the change in pH when a little base or a little acid is added into it. And mainly, why is it called an acidic buffer? Because mainly its pH, after it has adjusted itself, the pH is mainly below 7. And that's why it is referred to as an acidic buffer. Now for basic buffer, it is formed from a weak base. Let's list weak bases. We know, yes, we have ammonia. What else? Think of. Can we have this? The cyanide, can it be a weak base? Which other weak base? Anyway, base is any compound that is electron rich. So now in this case, our weak base such as ammonia and its conjugate acid, or its salt that is formed by reacting it with a strong acid. such as ammonia solution and ammonium chloride. Okay? If you have your solution that has both ammonia and ammonium chloride, okay, it's one solution with both ammonia and ammonium chloride. Now the solution behaves as a buffer solution. And why is it referred to as a basic buffer? It's because its pH is usually above 7. So that is a buffer solution. And these buffer solutions are important in industries, important in life, important. For example, think about yourself. You must maintain your internal environment constant, including pH. Okay? But usually you produce too much carbon dioxide. Okay? So this carbon dioxide, it would react with water to produce carbonic acid, which would dissociate to give you hydrogen ions that would alter the pH. But now because you have there are three systems. We shall study them in homeostasis probably tomorrow. Because you have three systems in your body that can regulate this, that can absorb these hydrogen ions, then usually maintain your blood pH constant. So let's see, how do these buffer solutions work? Let's talk about the action of an acidic buffer. Now consider a weak acid. Okay, let me use some permanent pen here. So consider a weak acid such as acetic acid, CH3COOH, and its ionizable salt, which is CH3 sodium acetate, which is CH3COO Na plus and minus. Now this solution, it is going to behave as a buffer. In that in aqueous solution, our acid, it is going to dissociate fully, or it is going to dissociate to give us, to attain this equilibrium, CH3COO, or it will attain this equilibrium. Okay, it will dissociate partially, did I say fully? Sorry for that. To attain this equilibrium. Okay, COO minus and then hydrogen ions. Okay, aqueous. Don't mind about my symbols. Okay, but they should be looking nice. Then also our conjugate salt or our conjugate base, being a strong electrolyte, it will also dissociate fully. It will ionize fully to give us acetate ions. Okay, acetate ions, this is plus. For it to ionize fully, okay, to give us the acetate ions, CH3, CO minus plus the sodium ions. Aqueous, aqueous and aqueous. Now, our solution is going to be in this dynamic equilibrium. Okay, you have your reaction vessel, or you put them in a beaker, for instance, and you have there the acid, the excess acid, and you also have there the salt. So within this beaker, it will have this equilibrium. Our solution mixture, our solution will have this equilibrium. Now, if you attain such a solution, or if you have such a solution that has attained such an equilibrium, if you add there a little acid, okay, addition, eh? Addition of a little acid, it should be just little. Oh, this is little acid, and the acid may be HCl. The HCl, it will dissociate obviously to give us, you are just adding little, not excess, so it will dissociate to give us hydrogen ions, okay, plus the chloride ions. Now these hydrogen ions, because you are adding hydrogen ions in the solution, it would tend, okay, to change the pH. But now, because you are adding hydrogen ions in this solution, remember we also had their hydrogen ions in the same solution. Now you increase the concentration of hydrogen ions. But remember, it attained an equilibrium. Now addition of hydrogen ions in this solution at equilibrium, it will disturb the equilibrium, that instead of increasing hydrogen ions, no, then more acetate ions, they will combine with the hydrogen ions that have been added in this solution mixture at equilibrium to form more undissociated acid. Okay? And the little hydrogen ions added, they are removed out of the solution. And the pH is maintained constant. Now, how about when we add there addition of little OH? Okay? If you add there some little base, maybe just a drop, still the pH won't change. In that the little base added, since you have there more undissociated acid, the little base added, it will react with this undissociated acid, okay, CH3, undissociated acid plus our little OH, okay, to produce what? To produce our acetate, okay, C minus, and our water, and the water in this case, it's a neutral molecule. And the OH ions have been removed from the solution, and so the pH is going to remain constant. So these buffer solutions, they resist changes in the pH. If a little acid stroke a little base is added. Also guys, yes, so let's see, how can we determine the pH of an acidic buffer? How can we determine the pH of an acidic buffer? Now from the Henderson-Hasselbalch equation, now these are two guys, Henderson and Hasselbalch. They came up, they sat down and did some good work, and they came up with an equation which we shall use to determine the pH of both an acidic buffer and the basic buffer. So from the Henderson-Hasselbalch equation, we can use it to estimate the pH of a buffer solution. And we should be able to derive, okay, that equation. So if we know the Ka of the acid, okay, if we know the Ka of the acid, then we can determine the pH. So how are we going to do it? So consider a buffer solution consisting of acetic ions and sodium acetate. I hope this space is going to be enough for us to do that calculation. So this solution, it is, we have sodium acetate CH3. Oh, sorry for that. Let me just erase everything. So it will be sodium acetate or sodium. It will be just simply CH. CH. Oh my god. So this is COOH, which will ionize partially to give us the acetate ions. Okay. Okay. The acetate ions plus the, my god, this is acetate ions plus the hydrogen ions. So this is aqueous. I'm going to rub this is aqueous, then this one is also aqueous. And then even the sodium acetate being a strong electrolyte, it also ionizes. Okay, the sodium acetate being a strong electrolyte, it will also ionize fully. For here we shall use full arrows to give us acetic ions. Okay, acetic or acetate ions plus the sodium ions. Now it will attain an equilibrium. It will attain an equilibrium in a way that if we determine the Ka from the expression of the Ka, which is simply the concentration of OH ions. Where is my mind? Okay, now I'm back from where the mind has been. So the concentration of acetic ions, okay, times the concentration of hydrogen ions, okay, everything divided by the concentration of undissociated acid, which is simply CH3 COOH. It should give us the KW, sorry, the Ka. But now here, since we have our strong electrolyte, okay, which also ionizes fully, you shall not assume, here your assumptions won't work, that the concentration at equilibrium of acetate ions is equal to, no, that one is wrong, and don't do that. Because see, you have these acetate ions both from the strong electrolyte and the acetate ions from dissociation of the acid. In fact, the hydrogen ions, the concentration of hydrogen ions is equal to the only acetate ions that dissociated from the acid. But remember this equilibrium, you have both acetic acid from the acid. So you have both the acetate ions from the acid and the acetate ions from the strong electrolyte. So that assumption doesn't work. Somebody is disturbing me. So here we shall not assume that the concentration is equal. So then what shall we do? Now we shall make H, the concentration of hydrogen ions, the subject of the formula, which is simply the concentration of hydrogen ions, okay, which is equivalent to, yes, it will be our Ka, not so guys, Ka times the concentration of our acetate and dissociated acid, okay, and dissociated acid, which is CH, sorry for that, minus, and everything divided by the concentration of acetate ions, okay, COO minus minus. Not so, guys. I hope everything is still moving on freshly, moving on well. Now, from this equation, remember I want the pH, and you already have the concentration of hydrogen ions. So if you have this, you have this, you have this, it means you can get the pH. Now, if we take the negative log, okay, of concentration of hydrogen ions, sorry for that, of hydrogen ions, it should be equivalent to the negative log of everything, negative log to base 10 of everything inside, which is Ka into the concentration of the undissociated acid. Sorry for the handwriting, but the good thing, whatever I say, sorry, whatever I write, I say it. Concentration of this, everything divided by the concentration of CH3 COO minus. I hope this is good. So everything negative log. Now here, this is simply mathematics. Let's apply the laws of logarithm. Okay, here. So laws of logarithm, where we brackets means multiply. So where we multiply, we simply add. And where we divide, we simply subtract. So let's open brackets. So this one we shall mean with pH. You know, negative log, it simply means pH, which is equivalent to negative log of Ka, negative log of Ka, not so, times. So here we shall add. So times, we shall add. Still negative log. The negative is maintained. Negative log, okay, of the concentration of undissociated acid, which is CH3, and then COOH. Now here we shall multiply minus brackets, okay, the negative log of what? The acetate ions. Concentration of acetate, which is CH3 COO. Oh, sorry for this, but it has not fit. And then you close brackets. Okay? You close brackets for everything. Now let me rub here so that we can get some nice room for calculating from. Yes. Now, this is our pH. Okay, which is equivalent to negative log of Ka, that is pKa. Are you seeing? That's pKa. So meaning if you have Ka, you just take the negative log of that value that is given. Everything plus our brackets. So this is minus, and then this one is minus. So this is going to be plus. So this is the same as writing it as log, okay, of constant. This is the same. This is plus, minus, minus. That is plus. So that is log of concentration of undissociated of the acetate ions, okay, minus, okay, I'm just the concentration minus the log of concentration of acetate or of the undissociated acid, which is COO plus. Sorry for this, and then you close bracket. Sorry for this, but good you are following. Now, this is the same as writing it. Now, let's remove the log. Where there is log, where there is minus, we divide. So the same as writing pH, okay, which is equivalent to pKa. This is simply mathematics, okay? Plus, log, we are opening brackets by putting log out, okay? Into the concentration of this, of the of COCH3, okay? C, this is simply mathematics, minus, and where we minus, we divide. So this one is going to be simply divide by CH, concentration of CH, okay? This is simply concentration of CH, COH. So we have applied laws of logarithm, okay? Yeah, in case you've gotten lost somewhere, it's okay. We can still repeat over and over again. You will drop it or you will unmute and ask. Or in case you want us to talk about somewhere, it's okay. Unmute and say here. Yes. But the rest is simply mathematics. Laws of logarithm. Somebody saying something?
PK, PKA
Yes, here.
obtained from where?
We've gotten pKa from where? Yes, that's good.
Yes,
That is a good question. Yeah, we've gotten pKa from where? From here. Negative logarithm of Ka. That's pKa. You remember pH? pH, which is simply the negative log of concentration of hydrogen ions. Okay, you remember this. So the negative logarithm, actually, let me simplify it. If we say negative logarithm of anything, it is the same as saying p anything. I hope that one makes sense. If we say negative logarithm of anything, it's the same as saying p anything. So if we say negative logarithm of Ka, it's the same as saying p Ka. Not so, guys. Yes, please ask anything you feel like it's bothering you.
let's see on that where we said pH equals log K, negative log K, and the logarithm, the row of logarithms.
Mm.
When we proceeded, like negative times a negative, I think it is a positive.
Yeah, here?
Yes.
Yes.
When we continued, we made it a negative.
No, I think basing on your question, the way I've understood, after this turning into a positive, you see this is the undissociated acid. Hmm? It is here, undissociated acid. And this is our salt, the CH3, okay? The COO minus, okay? Now, after this turning into a plus, you see here, it is the one that came first, and then minus log of C now of the undissociated acid. Are you seeing? Are you seeing? Yes. And rows of logarithm, if you have logarithm of the same base, this is to base 10, even this is to base 10, then it is simply where we are subtracting logarithm of the same base, we divide. And it's what we have just done here. So I hope it's really good. I hope it is really good. Guys, feel free to ask. Feel free to ask anything. Then from that, I wanted to rub. Yeah, I wanted to rub. Then from this, we shall make some assumptions. And the assumptions are, remember you are mixing, you see, you have acetic acid, which is a weak acid, and sodium acetate, which is a strong electrolyte. Square this one ionizes fully to give you acetate ions. Okay, COO minus. And this one is a weak acid. And as if that's not enough, because of you already have the acetate ions in the solution, so even its ionization is going to be reduced. It is going to be reduced. So that the concentrations, so the assumptions here, we shall assume that all, not all, but the concentration of the acetate ions that are produced, okay, in this acidic buffer, the concentration of these ions is equal to the concentration of the salt that is added. And which salt? Sodium acetate. So in other words, if you are given 0.1 molar sodium acetate and you've added 0.1 molar sodium acetate in acetic acid of a known concentration also, maybe it is also 0.1 molar, then the concentration of the salt here, since it's a strong electrolyte, sorry for that, but if the acid is 0.1 molar and the salt added is also 0.1 molar, then we shall assume, since this is a strong electrolyte, the concentration of the acetate ions, it is assumed to be equivalent to the concentration of the salt, okay, which is also going to be 0.1 molar. Similarly, the concentration of the undissociated acid that will remain at equilibrium, okay, that will remain is assumed to be equivalent to the concentration of the acid that was used or that remained, which is equivalent to 0.1 molar also. If the acid is 0.2, then this one will be 0.2. And now, you know the pKa, you know the concentration of the salt, you know the concentration of the acid. You simply substitute in here and get the pH of the basic solution. So generally, the pH or the Henderson-Hasselbalch equation, therefore, it is simply pH. Let me write it with this pen. Okay, it is simply, okay, let me leave it with this. pH, okay, is equivalent to pKa plus logarithm to base 10 of the concentration of the salt, okay, divided by the concentration of the base of the undissociated acid. Sorry for that. And if you do this, trust me, you shall be able to obtain the concentration of the buffer, of the acidic buffer given. Let's do some examples. You try out that example and see. So this one is simply, you are given, let's do it together. They have given you the pH. Now we want us to calculate the pH of the buffer solution that consists of 4.1 grams sodium acetate per liter. Are you seeing? And a 0.1 molar ethanoic acid whose Ka is 1.7 times 10 power negative 5.